Welcome to iqpod.io, where Ava and David, your expert AI hosts, bring you the latest developments in the neural rendering and 3D reconstruction field. They delve into significant papers, offering detailed analyses and engaging in thought-provoking discussions about their implications.
Today we're delving into the paper titled 3D Gaussian Splatting for Real-Time Radiance Field Rendering. It's a mouthful, but stick with us as it represents a significant advancement in computer graphics.
Right, David. I've heard a buzz around this topic. So what exactly is 3D Gaussian splatting, and why should we care?
Great questions, Ava. It's a method introduced for representing 3D scenes that potentially rivals neural radiance fields, commonly known as NeRF. NeRFs took the field by storm for its novel view synthesis capabilities, that is, creating new images of a scene from viewpoints never physically captured before.
Okay, but why is this 3D Gaussian splatting coming into play now?
Well, although NeRFs perform wonderfully, they require heavy computational lifting and aren't real-time, limiting their practical applications. Enter 3D Gaussian splatting, which promises to address some of these limitations, notably rendering speeds.
I see. So the main problem they're tackling is speed without sacrificing quality. And how do they propose to do that with this method?
Exactly. They use 3D Gaussians. Think of a cloud where each droplet represents potential parts of a scene. By adjusting how these droplets spread out and combine, we create a full image. The magic here is that each Gaussian is a simple mathematical function. It's like a building block that can be easily manipulated and efficiently calculated.
Fascinating work. Now, what has been done before in this area that sets the stage for this paper?
The predecessors to this method, namely NeRF and its variants, have been about leveraging deep learning techniques to synthesize highly realistic images. However, they rely on neural networks, which, while powerful, are computationally intensive. This new work sidesteps this by proposing a method without these networks, optimizing a scene from 3D points directly.
Hold on. If they aren't using neural networks, does this affect the quality or the types of scenes they can handle?
That's a pertinent observation. While you might think so, the authors have crafted their method such that it preserves the high quality of NeRFs while drastically increasing rendering speed. This opens the door to using it in real-time applications. Think augmented reality, virtual reality, and interactive gaming.
Impressive, but what stands out as truly new in this paper?
They make several novel contributions. Firstly, the method is not just faster, it's competitive with the fastest radiance field methods out there. Secondly, it respects the properties of volumetric optimization, ensuring that the richness and fidelity of a scene are maintained. Thirdly, and here's the kicker, the rendering happens in real time. That's a game changer for potential real-world applications.
And in the grander scheme, how does this advance the field?
By departing from the commonly held belief that continuous neural network-based representations are necessary for high-quality radiance field training, they've pivoted the focus towards optimization and rasterization approaches that could reshape how we approach real-time graphics. Plus, it paves the way for fresh research, exploring the integration of explicit, fast compute methods with the realism we demand today.
That clarification helps. Now I can appreciate the shift they're proposing in the field. I'm intrigued to see how they've implemented this method and the implications there. Diving deeper, David, let's talk about how the authors of 3D Gaussian Splatting for Real-Time Radiance Field Rendering put their method to the test. What kind of experiments did they conduct to prove the efficacy of their approach?
They meticulously designed experiments to validate both the performance and the quality of their method. They compared Gaussian splatting to existing state-of-the-art NeRF methods across multiple datasets. The datasets varied from synthetic scenes, which are well-constrained and ideal for testing, to more challenging real-world scenes that exhibit complexity and irregularities.
So a broad range then, giving a comprehensive picture of how it performs under different conditions. Now, what conclusions did they manage to draw from these results?
Their results demonstrated that Gaussian splatting significantly reduces rendering time while closely maintaining and sometimes even surpassing the visual quality of NeRFs. That's groundbreaking because it delivers on the promise of real-time rendering without taking a hit on the photorealistic quality that NeRFs are praised for.
Did they provide an explanation for why they achieved these results?
Indeed, they did. The crux lies in their optimized implementation and the simplicity of the Gaussian primitives. By using 3D Gaussians, they essentially allow more informed and strategic placements of points within the scene. This creates a rendered image much faster than the iterative sampling we see in NeRFs. In short, it's the mathematical elegance of Gaussians meeting the brute force of optimized computation.
And about the ablation study, which components did they decide to tweak and what were the findings?
In the ablation study, the team tweaked various aspects such as point initialization, the use of spherical harmonics, and the adaptive density control, which included splitting and cloning strategies. The findings were revealing. For example, they found that initializing points using SFM provided a better starting point than random initialization, as one would expect, given the SFM points are inherently informed by scene structure.
What about the appendices? Do they offer additional insights?
The appendices are packed with technical gems. They provide the detailed gradient computations necessary for the implementation, which is essential for those looking to replicate or build upon this work. There's also an extensive optimization algorithm that details how the adaptive control precisely fine-tunes the point cloud.
After all this technical deep dive, what's your favorite part or technique from the paper, David?
What I particularly admire is the fusion of classic computer graphics techniques with modern optimization methods. It's not just another iteration on neural networks. It's a bold step back to the basics, reimagining them with powerful contemporary computational strategies.
I have to say, my attention is captured by the potential this method shows for interactive applications. The thought of using this for AR or VR where real-time rendering is paramount gets me quite excited about the future possibilities.
That excitement is well placed, Ava. This paper does more than extend the boundaries of current literature. It invites us to rethink those boundaries altogether.
And that's a wrap on our discussion of the paper by Bernhard Kerbel, Georgios Kopanos, Thomas Leimkuhler, and George Dratakis from INRIA, Université Côte d'Azur, and Max Planck Institute.
It's work like this that keeps us looking forward to what's next in technology and computer graphics. Remember, this episode was generated by an AI, so there might be some inaccuracies.
If you have any questions or feedback, we'd love to hear from you. Drop us a line at questions@iqpod.io.
Until the next episode, keep pondering the possibilities of real-time rendering and the future it holds. Goodbye, everyone.
Goodbye.